everybody, the purpose of this video is to get you a solution to the Chuck-a-Luck quiz. I posted some quizzes, one of which was tied back to a homework problem. Chuck-a-Luck, if you don't remember, is the Vegas game where you roll 3 dice and you bet on one of the numbers and you get certain payouts based on how many of those numbers come up on the dice. So I think we bet on 5 in the homework. You pay $1 to play. If no 5s show up, you're going to lose the $1. If one of the dice comes up 5 and the other 2 don't, you win back your $1, so you get nothing and you average nothing. If you get 2 5s, you'll get $2 back, which means you clear 1. And in the original game, if you roll all 3 5s, then you get the big payout of 10 to 1. So you end up actually profiting $9. But the point of this problem was to see if we can adjust the payout for the $9 or for the 3 5s to make the game statistically fair. We'll come back to that in a moment. So that used to be $9. Now it's going to be X. And technically speaking, well, we'll come back to what that means in a second. We have to deal with an extra $1 as far as we have to pay out $1 more than technically should be, because we have to cover the cost. Because this is actually technically 0 minus 1, 1 minus 1, 2 minus 1. So this would be X minus 1 technically, but we'll just add the extra $1 back on at the end and just keep that in our mind while we do it. Here are the probabilities of rolling the various arrangements of 5s. We calculated all these in class together. Super fun, super fun. That was the day we lost network power and we couldn't use the simulation to do it, which made it even more fun. So a lot of students get kind of stymied by this problem because we get so used to using our technology and running things through one of our stats that we forget that you don't always have to do that, or sometimes you can't do it. For example, right now you can't do it that way. You have to crunch it this way manually. So you have to use the old idea that the average in a distribution is equal to the sum of the products of the random variables and their individual values. So I'm going to make a little P of X column right here. Actually do that in a different color so it stands out. So X being -1 times the P of X of 0.571 is going to give us negative 0.579. What that means is whatever the average ends up being, that much money is contributed by the losses. So we're going to lose 57.9 57.9 cents on average per $1 bet. Now we have to add back some money from that to get our average back. And we're getting the average back all the way to 0. So basically we have to make up this loss here. Now nothing's going to be made up here, because if you win back $1 and bet $1, that's nothing towards your average. Here you're going to win back 0.069. So here we've got a little bit of money back coming back from this. The trick is this one. This one contributes a very small percentage, 0.006, but it's multiplied by this beautiful X variable. And that's what's going to control keeping the average fair. So in order for it to be fair, where's my green chalk? In order for it to be fair, you have to have the absolute overriding average be exactly equal to 0. In Vegas, it's negative. It needs to be negative because you have to lose money on average for them to keep the lights on all the time and to pump water in from Los Angeles. So what we have to do is add up all of these results. So we're going to add up that negative 0.579, 57.9 cents lost, plus the positive 0.069, plus this guy, 0.006x. I'm truncating these. I'm rounding them off to the nearest thousandths place just to get the point across. Then we got to do is solve that bad boy for x. So we'll crunch that over here. We're going to have, let's see, we're going to have to add that to this side. So 579 minus the 0.069. And we're going to divide that. So that ends up being 51 cents right there, these two terms. And we're going to divide that by 0.006. And that ends up being 85. So X here ends up being $85, which means technically speaking, you'd have to be paid back 86 because you'd have to clear 85, right? So if this is 85 bucks, they'd actually have to give you 86 to 1 odds to knock the game down to statistically fair. Now, I know depending on how you rounded, some of you guys might not get exactly $85, and that's fine. The key is, think about that. Think about how ridiculous that is. I mean, I remember in class when I said the payouts for these were 0 to 1, 1 to 1, 2 to 1, and then 10 to 1. A lot of you were like, whoa, that's awesome. And that does seem pretty awesome, right? I mean, it seems pretty rad to get 10 to 1 payouts back. But the trick is, with a 10 to 1 payout, your average still ends up being negative. So there's really nothing to be excited about with a 10 to 1 payout. So with an 85 to 1 payout, the game becomes fair. Now, why do the casinos love that? The casinos love knowing that because they can then say, okay, so with a 10 to 1 payout, I believe the average is something like negative 47 cents, I think is what it ended up being. I had it written down at some point. They can say to themselves, all right, let's increase the payout of this one to 20 to 1 instead of 10 to 1. That way, if you bet $1, you'll get 19 bucks back. And that might actually draw more people into playing the game, right? If you have a 20 to 1 payout. And the increased revenue from those games, of course, goes back to them, because even with a 20 to 1 payout, the average is still going to be negative until they get to an 85 to 1 payout. Then, because it's still a randomly very, very unlikely event, $85 will get you back to 0. Anything else below 85 still creates a negative net average, which means you're paying Vegas on average. Isn't that cool? Totally cool. And this is what actuaries do all day long. They figure out how much money they know this based on statistics and charts and stuff like that. They figure the break-even point out, and once they know the break-even point, they can figure out what everything else has to be balanced wise to ensure income. It's super fun when you think about it that way. So anyway, I hope that was half as enjoyable for you as it was for me. There's an extra credit problem on there that says, okay, now I want you to keep the payouts exactly what they were, which is nothing 1, 2, and 10, but adjust the ante. If anybody wants to see that, there's not really enough board here to do that. It's definitely an algebraic kind of construct. But I will have you think about it this way. If you want to do it algebraically, I want you to also think outside the algebra box a little bit. To answer those extra credit problems, think about it this way. When the payouts are the way they are, 0, 1, 2, and 10 times your bet, you end up averaging negative 47 cents per game, which means you walk up with $1, you hand Vegas $1, and then they take 47 cents of it and you walk away with 53. So that's kind of like negative 47 cents profit. So think about the ante. You're anteing $1 and then on average losing 47. Well, in order to make the ante fair, where would that 47 cents have to go? Think about that. That's a neat non-algebraic way of figuring out the answer to that extra credit problem. You can also do it algebraically, of course. It's always, maybe, algebra is a beautiful thing, but you can also knock it out non-algebraically too. Hope that helped.